Hi everyone, this is José with Jelly, and in this video I will be talking about what the z-score is and some of its practical uses. I'm assuming that you're familiar with three concepts, like measures of central tendency, such as the mean, measures of dispersion, such as the standard deviation, and the 68, 99, 99.7 empirical rule. So we're going to start with an example. Every November, Gallup poll conducts a survey on American adults. They ask questions about health, including weight. Gallup reports that between 2013 and 2017, the average American adult weighed 177 pounds. So we're going to write that down and indicate it with the Greek letter mu. Now, for the sake of this video, we're going to assume that we have information on the entire adult population. If we plotted this information, we would get a frequency distribution that would look like this. And this is our normal distribution, or bell-shaped curve. Some people call it like that because of its shape. Now, the key important thing here is that this curve is centered around the mean. So I'm just going to write here 177. And this shape is telling us two things. The majority of the population is concentrated in the center, and there are fewer people who weigh more and fewer people with a very low weight. Now, the shape of this distribution is given by the standard deviation, which in this case we're going to denote with a Greek letter sigma, and we're going to assume that it's 20 pounds. Now, if you remembered that I mentioned the empirical rule at the beginning, this is where we're going to use it. So we know, according to the 68, 99, 99.7 rule, we know that if we move one standard deviation to the right of our mean, we're going to include let me move one standard deviation to the right and to the left. So we're going to have here 197 pounds, and over here we have 157 pounds. Okay, so we know that if we've moved one standard deviation to each side of our mean, this is going to include 68% of our population. If we move an additional standard deviation to the left and to the right, we have 217 pounds here, and to the other side we have 137. And this is two standard deviations, two standard deviations. Finally, let's take a third jump, and this would be 3 standard deviations to either side. So we end up here with 117 pounds, and on the other side we have 237 pounds. Now, this is very useful and it has a lot of applications. The problem is, what would happen if we have a value in between one of these marks that doesn't quite fit in between the standard deviations? So let's say that we have a person X here who weighs 150 pounds. So at least we know that this person would be right here in between 1 and 2 standard deviations away from the mean. But if we want to extract information from this person, or where this person is located on the distribution, we would have to use our z-score. And I'm just going to write the formula here. Z equals x minus mu divided by the standard deviation. So we already have two pieces of information. We already have mu, which is our mean, 177 pounds, and we have our standard deviation, which is 20 pounds, or sigma. X is this value, 150, for which we are extracting information for, and z is the rescaled value. Okay, so let's assume that we standardized or rescaled the entire distribution. So I'm just going to plot what this new distribution would look like. So it looks pretty much like the first one, but the thing here is, and I'm going to project this mean down, the thing here is that now our mean is 0, and our standard deviation is 1. So that means that for each jump in the original graph, we now have a 1-unit jump in the standardized graph. So here's to the right, and then the same to the left. So we have -1, -2, and -3. So something to keep in mind, the original normal distribution is measured in pounds, while the standard normal distribution is measured in standard deviations away from the mean. So let's go back to our example and let's solve this formula. So we know that x is 150. That is our hypothetical value in this case. Minus the mean, that we know it's 177 pounds, divided by sigma, which is 20 in this case. So our z is negative 27 divided by 20. And this ends up being negative 1.35. Okay, so the big question is, what is this number telling us? So remember that I told you that we obtain the standard normal curve by applying this formula and rescaling the entire variable. So if we plotted this z-score in our graph, it would be, and let me use a different color so that you can clearly see, it would be right here. And this is our z, negative 1.35. So all z is the number of standard deviations away from our mean of 0. Now we can ask another question here. We can ask, what is the proportion or the probability of people with a weight lower than 150 pounds? So it would be this area that I just shaded. People with a weight or to the left of a z of negative 1.35. And we can do this, or we can solve this with the standard normal, because the entire area below the curve equals 1. That means that 100% of the population is included below the graph. Okay, so I'm just going to use mathematical notation here to denote this second step. So we're trying to find the number, or the proportion of people with a weight lower than 150 pounds. Now this is in normal notation, and if we want to express it in standard normal terms, this would be the probability or the proportion that z is below negative 1.35. Okay, but now to estimate the area under the curve, or that I've shaded here, we're going to use the z table, or the normal proportions table. What you can find in this table is the standard normal probabilities. So what we're going to do is, on the first column, you're going to look for the leading digit in the first decimal. And then on the first row, you're going to look for the second decimal. At the intersection of both, you're going to find the area under the curve, or the area that is shaded in this case. You'll find that the probability here is 0.0885. If you multiply this by 100, you'll get a probability of 8.85%. So this means that 8.85% of the population weighs less than 150 pounds. Or there is a probability that any given person, there's a probability of 8.85% that any given person weighs below 150 pounds. Now the nice thing here is that we could also ask the question about the remaining part of the curve. So we could ask a question like, what is the probability that a person weighs more than 150 pounds? And because the entire area under the curve is 1, all we have to do is subtract the original area, so the 0.0885 from 1. Whoops. Here, 0.0885, and this equals 0.9115. Again, if we multiply it by 100, we know that the area on this side equals 91.15%. Keep in mind that these are some very basic examples. Examples can get complicated very easily, so if you have any questions or would like to receive extra support, you can call our office at the Graduate Research Center, and we will be happy to work with you. Thank you. Until next time.